Time, everyone. Good day and good time, everyone, from all over the world. Welcome to the EMI Dynamics Committee seminar series. Along with my colleagues, Professor Marian Gutierrez Soto and Professor Manolis Chatsis, we are very happy to host this event. This seminar series has been started by Professor Eleni Chatsis, the former chair of the committee, and we are proud to continue the legacy and hopefully have seminar series, monthly seminar series for the committee members. So before introducing our host, I want to take a few minutes and just make a few remarks. At EMI Dynamics Committee, we have several activities going on. I would encourage everyone to please check out our webpage and become familiar with the different activities that we are pursuing. I'm sharing the link in the chat box with everyone. If you are not part of our committee, we'll accept new members. There are conditions for membership, so please check if you meet those conditions, and if you meet, then there is application process. We will be happy to admit you as a part of our committee members. Then you can officially contribute in other committee activities. Also, another small remarks is that so the EMI conference is open. The abstract submission deadline is December 31st, is end of December. I shared the link also. The conference would be in Chicago this year. So please consider participating in the conference. Also, the committee is sponsoring many mini symposiums that you can submit your abstract to it. Very well. So with this small announcement and without further ado, I would like to introduce our speaker, Professor Suparno Mukhopadhyay from ITT Kanpur. And thank you so much, Suparno, for being with us today. Suparno is going to talk to us about his work on state parameter estimation and optimal input-output location for monitoring of structural systems. With that, thank you so much, Suparno. The floor is yours.
Thank you, Hamid, for the nice introduction. So I will talk, and so I will, as Hamid said, I'll be presenting on the state parameter estimation and optimal input-output locations for monitoring of structural dynamic systems. So it's mainly on structural identification, on which I mostly work on. So in today's presentation, what I am going to mostly focus on, what I'm going to mostly focus on. So as you know, structural identification, just to introduce, is it's an inverse problem. So you have a physical structure, so from which you are collecting some measured responses. Maybe you know the excitations, and the aim is to identify a model of that system. The model can be the form of the differential equation, which we'll not talk about here, or it can be that the differential equation is known. We are trying to identify the parameters which are defining that differential equation. So what we like the intention is that, or the object, or the intention is that the identified parameters are presenting a true representation of the structure in its current state, and provides us with a model of the structural dynamics. It can be used for prediction using the identified model, and any changes in the identified parameters over time can help us monitoring changes in the system, such as structural damage. So while this is a very, a lot of work has been done in the last 35 years, in the last 3.5 decades in this field, what I am going to mostly talk about are one approach to identify the parameters, which is based on the uncentered Kalman filter and some of its variants. And then I will talk a little bit about modal identification leading to physical, and using modes to identify physical parameters, and related to that, the identifiability of linear systems. And then finally, if I have some time, I'll talk about how to locate the sensors and inputs correctly, so as to maximize the information about the parameters we want to identify, and thereby minimize the uncertainty in the parameter estimates. So I'll start with the uncentered Kalman filter and variance for physical parameter identification. So we'll start with the state space representation. Many of you must have seen this. So we have suppose we have a linear system. We have the states which consist of the displacement and velocities, and we can define a state space model of the system in continuous time. We can then discretize it and have a discrete state space model of the system. The classical Kalman filter actually will work with this model. And knowing the system matrices A, B, C, D, we try to identify the states, we try to predict the states of the system, knowing as the measurements come along. Okay. If it's a nonlinear system, we can do a similar thing. We can similarly define a state space model for nonlinear systems. And if the objective is to identify parameters of the system, we can augment those parameters to the state matrix, as is done here. And then so identify the states using the Kalman filter framework, okay, including the parameters. Okay, so that is what we will be talking about in the beginning. So the state estimation problem, as the Kalman filter does it, we can represent it in this way very simply, that we have a prior estimate of the state based on the data available till the k-1th time instant, and then using the process equation we try to have a priori estimate of the state, okay, of the density function of the state. And then as the measurements come, we try to update the a priori PDF to the a posteriori PDF of the state for the next time instant, and so on, and we proceed in this way. So for the linear Kalman filter will work in this way. Now, if the system is nonlinear, okay, or if in the identification problem, even for a linear system, if you are casting it this way, then the identification problem becomes nonlinear because you neither know the states nor you know the parameters. In that case, we have a nonlinear system, and just to evaluate these density functions or their means and covariances becomes a very difficult problem to exactly evaluate those. So we look for suboptimal methods to do that. Well, the Kalman filter is an optimal method in the sense that it's the Kalman gain, it tries to estimate by minimizing the posteriori covariance. Here, because of the difficulty in solving this integral, we try to look for suboptimal methods. And this one of the way of doing this problem will be to linearize the underlying nonlinear differential equations. However, linearizing has a problem. For example, say you have a random variable x which is normally distributed, and I do a nonlinear transformation on that, which is y equal to e to the power of x. So y, as we know, will be log normally distributed. But if I linearize y, what I am essentially going to get is a shifted version of the original distribution x. So it will be a Gaussian shifted Gaussian essentially, whereas the actual distribution will be much different. Okay. So linearizing has this problem, and linearizing the Kalman filter for nonlinear problems has led to the extended Kalman filter, and we will see some applications of this. But linearizing has this problem, especially if the uncertainty is very high. So another approach will be to take a lot of samples of x and propagate all of them through this nonlinear transformation, and then get the distribution of y. So there may be many methods to do that. Now, one way to do it will be is the uncentered transform, where you deterministically, instead of randomly choosing different x's, you deterministically choose a bunch of those points, which we call the sigma points. And if x is n-dimensional, you need 2n plus 1 sigma points, and then you propagate them through the nonlinear transformation, and then you compute the mean and the covariance of the transformed variable. So this computation of the means and variances involves certain weights which are chosen so that the mean and covariance that we are calculating at least have a second order accuracy. So if you see, what I'm trying to say is that suppose this is the actual sample, and you in the true mean and covariance will be something like this as you propagate all the points through the nonlinear transformation. Whereas if I'm linearizing it, I get something like this, okay, where the mean and covariance is widely off. Whereas if I choose the uncentered transform, I choose a certain points, not random points, but certain deterministically chosen points, and propagate them to a nonlinear function, then what I get is for the transform variable, I get a mean and covariance which is quite near, okay, the true mean and covariance. So the mean is the center point, and the covariance we are denoting by this circle around it. So applying this uncentered transform to our structural dynamic system, the nonlinear system. So we have a nonlinear state equation, nonlinear process equation, and a nonlinear measurement equation maybe. We start with an initial guess of the state and the initial guess of the covariance matrix of the state. We then generate the sigma points as necessary, propagate them through the nonlinear process equation, nonlinear state propagation function, and then compute the mean and covariance, and now the a priori estimate of the mean and covariance of the state. Okay, just like in Kalman filter, and then we again we do the same for the predicted measurement. Now we are at time step k-1. We predict the measurement at time k using the same uncentered transform. And then from that, we can, once the actual measurements come in, we can we compute the Kalman gain. And then once the Kalman gain is computed, we update our state and covariance, the a priori estimates of the state and the a priori estimate of the state covariance matrices. So this is just one example, a simple numerical example of the uncentered Kalman filter. You have a 2 degree of freedom system, a 2-story building, say, subjected to an earthquake motion, and suddenly at 10 seconds, we had a drop, suppose, in the steepness of the first story, K1. So if you look at it, we are comparing the true, we have a sudden drop, and the UKF and the EKF. Both the UKF and the extended Kalman filter can catch up, can detect the sudden drop in the steepness. Whereas if we look at the damping coefficient, the EKF does not converge, whereas the UKF converges. So that is what I was talking about, that if the uncertainty becomes high, then sometimes the linearizing will not work, actually. May not give that accurate results. So while the UKF seems to be a very nice technique, and it has grown to be very popular, there are certain limitations. One, that it is a very costly technique with that the propagation of the sigma points to the nonlinear function being the computationally costliest step. So recently, Papa Constantiniu and his students from the PSU from Penn State has developed, based on the works of Julier and Ullman, a variant of the UKF, which is the spherical simplex uncentered transform. So in the uncentered transform, you are choosing the sigma points all about this, whereas in the spherical simplex, you are choosing the sigma points in a sort of a simplex polygon in the sphere. So while in the conventional uncentered transform, you need 2n+1 sigma points, in the spherical simplex, you need only n+2 sigma points without losing the accuracy significantly. They have an equivalent accuracy. And with this reduction of the sigma points, basically leads to a 50% reduction in the computational efforts. So this limitation of UKF, the traditional UKF of being computationally very costly, to a significant extent is sorted out by this spherical simplex UKF. And in the remaining presentation, I will basically be using, in the examples that I will show, I'll be using the spherical simplex UKF. Another issue with UKF is that the initial choice, it is very sensitive to the initial choice of the covariance matrix. So to account for that, or to address that, in the conventional UKF, it requires significant tuning of the mean of the initial choice of the state vector and the covariance matrix. To account for that, what we can do is we can incorporate some model-informed constraint bounds while implementing the UKF. So these model-informed constraint bounds are simply say the steepness cannot be negative, the damping cannot be negative, and so on and so forth. So this leads to a method which is called the truncated UKF, the truncated uncentered Kalman filter, where the a posteriori PDF is truncated before computing the next a priori PDF. So using the model-informed constraint bounds. So this can handle linear constraints on the states, and the states include the parameters in our augmented state vector. So it can incorporate the constraints on the parameters, and it sequentially incorporates each constraint. So what it essentially does is it transforms first the state vector to a vector which has only one element which is populated and the others are zero. Okay, so basically it takes it to a vector where everything else is basically uncoupled, and then applies and the constraints are similarly transformed, and it applies the constraint bound on this transformed vector. This transformed vector, because it's weighted by this, the inverse of the covariance matrix, square root of the inverse of the covariance matrix, has mean zero and covariance identity. So once you have this transformed vector, you can apply the the constraint bound. Suppose we have bounds on the constraints that a lower bound and upper bound on this transformed vector. Truncate the PDF of this transformed vector θ1, the first element. Normalize it to a unit area. So this was the original PDF. These were the bounds. So we truncate it and then we normalize it to a unit area. And then we know the mean and variance of this truncated normalized θ1, and then we retransform that back to the original state vector Z. So that's one way of handling constraints. Another way of handling constraints is that you have, say, linear inequality constraints on the states. And as many of you may know, that the Kalman gain, as I said also initially, the Kalman gain is computed in the classical Kalman filter and KF by minimizing the posterior covariance matrix. So while minimizing the posterior covariance matrix, you can put in the constraints here. One can put in the constraint equations here and solve a unconstrained optimization, solve a constraint optimization problem. So the Kalman gain is computed by minimizing the posterior covariance matrix subject to these constraints. Okay. So in this way also the constraints can be incorporated, and this is called the constraint gain uncentered Kalman filter. So we'll see some applications of these. We'll start with the numerical application, a 4-degree of freedom system, where we have 4 Bookwen elements basically over here in all the 4 stories basically, in all the 4 links. Okay, so the parameters that we want to identify are the 4 stiffnesses, 4 damping ratios, and the Bookwen parameters. So we are not including pinching and degradation effects here. It's the simple Bookwen model. So we put the constraints that the stiffnesses are greater than 0, the damping coefficients are greater than 0, and that it's and certain constraints on the Bookwen parameters, to define the hysteresis depending on the system. Okay. And we try out different. So to test the uncentered Kalman filter, we try out the simplex Kalman filter, the CJUK, which is the constraint gain one, and the TUK. Both the CJUK and TUK are applied in addition to S3F. So this is S3F, the spherical simplex Kalman filter. This is spherical simplex plus CJUK, and this is spherical simplex plus the truncated uncentered Kalman filter. We try different levels of uncertainties or in the initial covariance matrix. So the initial covariance matrix of the states. So that's why we have the first 1, 2, 3 cases are for a lower uncertainty in the initial covariance matrix. 4, 5, 6 is for a slightly higher, and 7, 8, 9 is for a even higher uncertainty in the initial covariance matrix. So this shows the increasing level of the initial uncertainties. And we plot here the cumulative probability distributions of the percentage error in the estimates. Okay. So if we look at it, as the uncertainty grows, okay, both the spherical simplex has a much higher percentage of error. Okay. Whereas the CJUKF, the constraint gain, also has errors, whereas the truncated uncertain Kalman filter is seen to perform the best amongst the 3. So while both the CJUKF and TUKF are incorporating the constraints, the TUKF seems to be more, at least based on this example, seems to be more or less sensitive to the initial choice of the covariance matrix. So if you compare these 3 curves. So now we also tried these 3 variants of the uncentered Kalman filter with a Bookwen model with including the pinching and degradation effects, and this could not be identified because of less sensitivity of the parameters to the data, or due to maybe some identifiability issues which we are currently looking at. But what we tried also was identifying, simulating the data, including pinching and degradation effects, while identifying using the simple inaccurate model, which does not incorporate pinching and degradation. So what we saw was, while, and here we are only showing the TUKF because the CJUKF and only the S3F could not work at all. They were just diverging, whereas the TUKF was still giving some performance. So what we saw was, while the estimates of the parameters were not converging, but the estimate of the hysteretic force deformation relationship and the hysteretic energy dissipation was still predicted quite accurately with this inaccurate model. So using an inaccurate model class, we were still able to get the hysteretic energy dissipation and the hysteretic force deformation relationship with reasonable amount of accuracy. Although the individual parameters, individual story stiffnesses, and hysteretic deformations were not correctly predicted. So we tried this on an experimental setup also, which is an RC frame, a 4-storied RC frame, which we progressively damaged by using scale ground motions of the Kobe earthquake ranging from 0.1 G to 2.4 G. And between each run of the ground motion, we used low amplitude white Gaussian noise, okay, to study the modal parameter, get the modal parameters and see to get the natural frequencies and the damping ratios and see how they vary with damage. So the first visible damage was observed at around 0.4 G, okay, and that can be seen from the natural frequencies and damping ratios that are estimated, that the natural frequency suddenly drops at 0.4 G, so it was a significant drop, and the damping ratio also shows a significant increase at 0.4 G due to increased energy dissipation due to the crack opening and closing effects. So using the uncentered Kalman filter, the truncated uncentered Kalman filter, also we could see, and we computed the energy dissipation from that, we could see that around 4 G it shows a sudden increase in the energy dissipation. Okay, and here again we did not include the degradation and pinching effects due to identifiability issues. We used the simple Bookman hysteretic model without the pinching and degradation effects. I'll show some more applications of the truncated uncentered Kalman filter. One is a train bridge system. So here we have a bridge which is modeled as a beam, a simple Euler-Bernoulli beam on which a heavy train is running, and the equation of motion will be something like this. As you can see on the equation of motion, that if the mass of the train is comparable to that of the bridge or is quite heavy, then this becomes a time varying system. Okay, a linear system, but a linear time varying system. So to see the performance of the TUKF, what we did also was we did a model identification of the system. So the mass matrix of the system changes with time, so the modes vary with time. However, we saw that the modes are not randomly, not suddenly varying with time. They show a gradual variation with time. So we modeled it using a ARX model with time varying coefficients. And within certain time windows, small time windows which are overlapping, we kept the coefficients constant, to basically replicate this thing, that they are not, the variations in the model parameters are not sudden or random. Okay, they are gradual variations. So what we did was, from the response, we swept a window across the entire response, and within each time window, we identified an ARX model. Now we excited those ARX models using impulse excitations. For the first window with an impulse excitation, and for the next window onwards using the past response from the previous window with 0 input, and then concatenated those responses to get a time varying ARX model of the system. And then again on that time varying impulse responses, we basically ran another set of sweeping windows. Within each window, we identified the modal parameters of the system using eigensystem realization algorithm. I will talk about this algorithm shortly. Okay, so for the first window, we identify omega 1, zeta 1, and phi 1, the mode shape, and the second window, and so on. Okay, so we did this experimentally in the lab on a simple beam structure with a running train on it. And here I show the identified frequencies. As you see that as the train goes over it, the frequency shows a dropping trend and then increases again. And the modes show these variations. So these gray ones are the modes identified at different time instance in the different windows. And the red one is the mean of those. Okay. And we compared it here with the identified from hammer tests. And what we identified from the hammer test on the bridge and the identified frequency of the bridge from the this ARX model compare reasonably well, 158.2 and 158.3 hertz. We also ran the TUKF algorithm on this data, and we try to identify the EI of this train bridge system. And based on that identified EI, we try to get the mode shape, and we compare the mode shape with the one that we have obtained from the autoregressive modeling, and as you can see, they compare reasonably well. So the third example I will show is on the rocking of unanchored objects, and Manolis is here, so we will use his we'll be using his model that he had proposed for rocking of rigid body on flexible basis. So the rocking started, of course, with Hausner's rigid body on rigid base, and then many people worked on it, and Charges and Smith's paper basically works with the rigid body on a flexible base and includes uplift and sliding and friction. So we'll be considering this model of rocking of an unanchored object, and we also studied what happens if there is body flexibility, and we'll be also considering this model from an identification point of view. So for these models, we know we use the measured displacements, and we try to predict the states using the rocking response. And this is for the rigid body on a flexible base. We compared the spherical simplex method and the truncated uncertain Kalman filter. Okay, and we limit the in the TUKF and the CJUKF we put some bounds on the soil stiffness and the soil damping in this case. And as you can see that the S3F basically blows off. Without any constraints, it completely blows off. Whereas the TUKF, while you include the constraints, although has some uncertainty, okay, tries to, still follows the true response in some sense. This is for the velocity. This is for we are measuring the displacements X, Y, and theta. And these are the estimated velocities, the estimated in the theta direction, X direction, and Y direction. Okay, and similarly, these are the estimated soil stiffness and soil damping. And again, S3F often, although it converges, but it often fluctuates a lot. Whereas both TUKF and CGUKF, converges to the correct values, in a much better way. So this actually shows the importance of including constraints while including constraints that we may know while identifying such systems which show a complex dynamics. This is for a flexible body on a flexible base, and again we compare only the S3F doesn't work here, so we compare only TUKF and the CJUKF, and the TUKF and CJUKF both converges in case of estimating the EI of the body. For the soil stiffness, the TUKF converges fast, and the CJUKF takes some time, but still shows a converging trend. So this was one thing that I wanted to talk about, using uncertain Kalman filter and certain variants of the uncertain Kalman filter, especially including constraints for the physical parameter identification of systems which show complex dynamics, such as time-varying systems, nonlinear systems, or rocking bodies. The next part I'll talk about is based on my based on things that I have done before during my PhD, which is on modal identification and identifiability of linear systems. So I'll first present the framework briefly. So you have the data, which is the input and the output, the measured data. The framework that we will follow, there are many ways of doing it. One that we'll follow is from the measured data, first identify a linear state space model of the system using certain techniques, which we will use the observer Kalman filter identification and the linear system realization algorithm. From the linear state space model, we can identify the complex eigenvectors and eigenvalues. And in case we have classical damping, we can identify the normal modes of the system. And from there, we will try to identify the physical parameters as the mass, damping, and stiffness matrices of the system. So first, coming to the state space model identification, the way we will cast it. So we have two methods which were developed, by Yuang, Fan, Hota, and Longman, and Vicario, Fan, Betty, and Longman in one in the early 90s and in 2014. One is when we know the input, we recast the state space model that we talked about, the discrete time space model, in this format by augmenting the output to this over here. So this is essentially like a ARX model. Okay. And from here, we try to identify the Markov parameters of the system. And if the input is not known, it's an output only situation, then you again recast it in this way, with the output here. And then you can identify the Markov parameters of the system, which instead of the B, it has the Kalman gain over here, essentially. So this Markov parameter is nothing but the pulse response of the system. So if you know the Markov parameters, you can then do in the eigensystem derivation algorithm, what you do is from the Markov parameters, you create the Hankel matrices, which are basically, you have these Markov parameters and you basically stack them in this way, y1, y2, y3, then y2, y3, y4. These are the different Markov parameters. And this Hankel matrix, you construct it, and then if you decompose it, for example, using singular value decomposition, from there you can get the CD and BD matrices. Of course, these are not unique because the decomposition is not unique, and this will give you only one realization of the state space matrices. And then you can create a shifted Hankel matrix, okay, which is basically you start from y1, y2, y3 in the H1, and the shifted Hankel matrix you start from y2, y3, y4, and then y3, y4, y5, and so on. So this, if you look, compare with the original, the first Hankel matrix, this is essentially has this AD sitting in between. It is multiplied by with this AD in between, the state matrix in between. So decomposing the earlier matrix, you had this P and Q, which are the observability and controllability matrices, basically. And since you have this AD sitting in between, you can basically compute the AD by taking the pseudo inverse of P and Q, okay, with the shifted Hankel matrix. And once you have these matrices, the state space matrices, AD, BD, CD, from there you can get the modal responses. Okay. So this has been used in a lot of cases. One example was the Wilson-Thomas bridge. It was used in 2002. And here we compare, I show the comparison of the measured and the reconstructed accelerations, where the way the reconstructed accelerations are from the identified model using the system, okay, using the OKID that we discussed. We recently used it also for machine tool monitoring, where we have very high frequency vibrations in machine tools. So we had this boring bar, and we took a video of this boring bar, and then using an edge detection algorithm, the canary edge detection algorithm, we got the displacement responses of the tip, and from there we tried to use we used OKID array to basically get the modal parameters and reconstruct the frequency response function of this bar. So this has basically found applications from large systems to very small systems with very high frequency systems like machine tools. Okay. So once you have identified, if the next step is to identify once you have identified the modes, if the next step is to identify the parameters of the physical parameters of the system, then one way to do it is that if you have a complete instrumentation, then what you have identified here, for example, here you have identified the state space model, and you have the eigenvectors and eigenvalues of the state space model. Okay. And this is your second order system. Okay. And these are the eigenvectors and eigenvalues of the second order system. So the matrix which relates these second order systems, eigenvalues and eigenvectors contained in psi, the eigenvectors in psi, and the state space models phi, that matrix T can be computed if you have it can be shown that if you have a collocated actuator sensor pair, a DOF with having both an actuator and a sensor, then you can uniquely determine this matrix. And once you have determined this matrix, you can compute the second order systems, eigenvector matrix. And once you have from the matrix of from the identified matrix that you are getting from the state space model, identified state space model. And once you have that, you can basically compute the mass, the entire mass damping of state space matrices, provided you have a actuator and order sensor at every degree of freedom. If only n degrees of freedom are instrumented with an actuator order sensor, you will get the reduced order matrices, only for those n degrees of freedom. Okay. Now, what happens if there is incomplete instrumentation? When the instrumentation is spatially incomplete. For example, say I have a 3 degree of freedom system where I only have an actuator at M1. I know the force applied at M1, and I am measuring the displacement or displacement at M1, for example. Then what the questions are: can there be multiple sets of parameters which will satisfy the measured data equally well? And what should be measured in this case to identify a unique set. So to answer that, for example, say in this case, if I have an actuator sensor at the first degree of freedom, we can identify the two systems, system A and system B, will give distinct responses, and hence they can be identified distinctly. Whereas if I had it at the second degree of freedom, then two different systems A and B will give exactly the same response under the same input, and hence there is no way to distinguish from the measured data U2 and Y2 the two systems A and B. Okay, so this is what we mean by identifiability, whether you have multiple models which fit your measured data equally well. Okay. So to do that, the way we can cast this problem is that, suppose, and this we will only do for shear type systems, suppose you have measured data, okay, at certain locations, how to find the complete mass normalized mode shape matrix, and what is the necessary information which will allow a unique normalization and expansion. Because once we have the mass normalized mode shape matrix, we can uniquely get the mass and stiffness matrices. Okay, so what necessary information will allow this unique normalization and expansion? So one way to normalize, which we developed, is called the input-output balance, which we term the input-output balance. Suppose you have, what we note that, that the inputs, when weighted with the mode shapes at the input locations, will create the modal responses, and the modal responses, when weighted with the mode shapes at the sensor locations, will create the measured responses. So then this can be cast as a least squares problem, where you compute the pseudo-modal responses, we call them pseudo-modal responses, under the inputs which do not have the mode shape components. And then you basically try to relate the measured input with the pseudo-modal responses through this matrix psi, which basically contains the squares or products of this mode shape components coming from the actuator locations and the sensor locations. And then you can get the mass normalized mode shapes at all the degrees of freedom where you have the instruments located, with the requirement that at least if every DOF has an actuator and a sensor, you can get the complete mode shape matrix, and the requirement is that there is at least one co-located actuator sensor pair. Now coming to, suppose you have actuator sensors at only certain degrees of freedom, what will be the conditions where you can expand them to the entire mode shape matrix? And there, for shear type systems, you can show that if two consecutive floors, or if the first or the top floor are instrumented in either of these ways, you can reconstruct the entire mode shape matrix. So if we instrument the first or the last or any two consecutive floors in between, we can estimate the complete mode shape matrix, and this will be a unique estimate, making the system globally identifiable. So we applied it on some experimental data where we had this is on the Los Alamos lab. We have this system. We treated it as a free phase system. We know the force applied here, and we know the acceleration here. So only F1 and U1 are measured, and we know the total mass of the system, and we reconstructed the entire, we identified the system, and this is comparing the measured input with what we have from the identified system, the estimated input from the identified system. And as you can see, they compare reasonably well. Another way to cast this problem will be to cast it as that whatever information we know about the structural topology, we use that and we develop a system of nonlinear equations in terms of the mode shapes and the structural parameters, and we try to solve that used to get the for example the mode shapes. Okay, so all the structural topology requirements and any other information requirements that we may have, we basically cast it into a nonlinear system of equations to get the mode shapes of this system. So in this case, for this nonlinear system of equations, we'll have we cannot say whether it will always have a unique solution, but there is a theorem which is called the implicit function theorem, which guarantees that at least locally the system parameters will be identifiable. For example, so what the theorem states is basically that if this nonlinear system of equations has a root at alpha star theta star, okay, where alpha is some vector of known parameters and theta the vector of unknowns, which are the elements of the mode shape matrix, and if at that root the determinant of the del G del theta is non-zero, then that's sufficient condition to say that around every alpha star theta, around that alpha star theta star, there is a unique theta for every alpha. So there is a unique solution of the unknowns for every known set of known vectors that you have, set of knowns that you have. So that means that in such a case, the sensor setup will at least assure local identifiability. Okay. So this nonlinear system, this method of identification we tried out on a non-shake table test that we had performed at Columbia University on this 4-storied frame, and we measured we consider that we know U1, U2, so we know the response of the first, second, and the fourth floors, and we know the total mass of the system. And again, this compares the measured and the estimated responses, and you see that they compare reasonably well. To illustrate the implicit function theorem and identifiability, we consider this system, okay, where we know the masses, we don't know the stiffnesses, we want to find out the stiffnesses. We say that we have two sensors which we'll place on any mass Mi and Mj. The question is on which masses Mi and Mj should be placed the sensors. When we use the implicit function theorem based test, we see that you can place the masses on 1 and 2, 1 and 3, 1 and 4, 2 and 3, 3 and 4, but not on 2 and 4. So we should not place it on mass 2 and mass 4. There the implicit function theorem fails. And if we try to see, if we place it on mass 3 and 4, okay, mass 3 and 4, so here and here, we are able to identify, two systems, one the true system and another system over here, but they are locally, separate. They are not continuous. So the system is locally identifiable, and the second system we can reject based on engineering judgment. Whereas if we place it on the instrumented degrees of freedom 2 and 4, if on the masses 2 and 4, where the IFT test has failed, we have a continuous, series of systems which will fit the data equally well. So the system is not even locally identifiable. Okay. So here the system is not globally identifiable, but locally identifiable. But here the system is not even locally identifiable for different values of, say, for example, the this component of the mode shape matrix. You get different values of the the different stiffness of the stiffnesses, many of which will make sense. You cannot throw out from engineering judgment, and they are very close to each other. So they are a continuous system of solution, continuous set of solutions. Okay. So the IFT test basically gives you a way to test if the system is locally identifiable or not. So finally, coming to the third thing that I want to talk about, which is the optimal input-output locations, and which is slightly, so we talked about how to locate the sensors to see whether the systems are identifiable, and we talked only about linear systems in this case, and shear type systems also, linear shear type systems. But now what we are going to talk about is how do you place sensors so that the uncertainty in the parameter estimates are minimized? So, and that has been shown before, that the uncertainty is minimized if you place the sensors at the positions where the information about the parameters that you want to identify is maximized. And one popular choice of the information is the Fisher information, which has been used before by Udvadia and Papadimitriou. And Papadimitriou has shown that it is related to the information entropy also. So we will look at different cases. One of them is the optimal input location. Suppose you are doing an experiment in the lab where you are hitting with a hammer and you want to find out where should I hit so that I get the the most the estimates of my parameters which are most certain, which have least uncertainty associated with them. So there, in this case, you can show that the Fisher information matrix is essentially proportional to the sensitivity of the responses with respect to the parameters, okay, under the assumptions that the measurement noise is zero mean white Gaussian noise, okay. So basically maximizing the trace of this. So the way we do it is by maximizing the trace of this, the Fisher information matrix, and are computed in this way, where we are basically integrating over the entire time duration of the response, the sensitivity of the response with respect to the parameters of interest. And we use some scaling here because the parameters we are considering are the model parameters. They have different magnitudes, so we use some sort of a scaling to make them dimensionless. So this sensitivities also can be computed analytically. For example, this is what you're getting from the modal superposition, where P is the actuator location and I is the ith sensor location, and you can compute this analytically by considering the pseudomodal response, where the pseudomodal acceleration response can be written in this way. It's the input minus omega j squared times the pseudomodal displacement, and the 2 zeta omega j times the pseudomodal velocity. And the pseudomodal displacement can, of course, be computed using the Helmholtz integral, and the pseudomodal velocity can be computed using Leibniz rule by differentiating the pseudomodal displacement. Okay. So then you basically get the pseudomodal acceleration, and then you have the expression for the measured response, in the physical parameters. Okay. So we applied this on some lab tests, on a laboratory test, on a laboratory scale truss, and as you can see for the mode 1, for example, as the information decreases, the estimates, the uncertainty in the parameter estimates, which we obtained using a Bayesian technique, that increases. The posterior uncertainty increases. The posterior covariance matrix's norm basically increases. Okay. So as information decreases, the uncertainty shows a increasing trend. What is also interesting is that if you incorrectly locate, for example, if I have the inputs located at the optimal DOFs, whereas if I have the input located at random at some other place, that affects your damage detection. And here we are doing a damage detection using a technique proposed by Bernal, using damage locating vectors. We introduced a damage in this, the 18th, in this element number 18, by replacing that element, with the element of reduced cross section. And if you use the input over here at 5, which is very near the the damaged element, you are not able to detect the damage. And here, if NCS is very low, that is the damaged element. Whereas if you have the inputs at optimally located locations, which are not necessarily near the damaged element, you are able to detect the damaged element. So the optimal locations of the input does affect your damage detection capability. Now, even if you have the input very near the damaged element, even then you may not be able to locate the damaged element, whereas optimal locations increases the chances of detecting the damaged element correctly. We'll move on to another example of this optimal locations, which is optimal sensor locations for a class of non-stationary base excitation, a building subjected to some non-stationary base excitation. We assume that the input time histories are unknown, but the power spectra of the inputs are known. Okay. And as the measurement parameter, we consider the sum of the non-zero eigenvalues of the measured portion of the output power spectrum. Okay. And using this, we will try to get this will basically, we'll try to maximize the information about the unknown parameters in this measurement parameter. Okay. So for the model of the input, we consider the input to be a filtered Gaussian white noise with some deterministic modulating function, okay, amplitude modulation. We note that the filtered Gaussian white noise, the spectra of the filtered Gaussian white noise will basically be a filter times the spectra of the noise. The spectra of noise will basically follow an exponential distribution that has been shown in earlier studies. And then, if that is the case, SX will also follow an exponential distribution, and we'll test this soon. But it can be shown that in that case, SX will also follow exponential distribution, and your measurement parameter, which is the trace of the output power spectrum, okay, which will basically be your SX times a function of the the parameters of interest times this amplitude modulation square, that will also follow a exponential distribution. Okay. So this actually shows this, that we use the Kanai-Tajimi spectrum with Hausner's amplitude modulation, and we generate an ensemble of motions, and here we show the distribution of SX, and here we see the distribution of the PS omega t at a given omega and a given time. And they both follow an exponential distribution as we hypothesized, or we showed. Now, knowing that the distribution of the measurement parameter is exponential, okay, we know that the Fisher information is basically the expectation of the derivative of the log likelihood, the product of the derivative of the log likelihood of this with respect to the parameters of interest. And the likelihood function is for an exponential, for the exponential distribution, we can write in this way. Okay, for the exponential distribution here, the likelihood function we can write in this way, and then compute the Fisher information from there. Okay, and after some algebraic manipulations, we can write the Fisher information in this form, which looks complicated. But again, here this TS is nothing but the the sensor location matrix, and this del SYY del theta m is basically the derivative of the output power spectrum with respect to the parameters of interest, which can be your modal parameters, or it can be the physical parameters, okay, like stiffnesses or damping ratios and so on. And these can be computed analytically. So we tested this on a shake table test that we did at IIT Kanpur, And it was found that, and we could see that actually that the uncertainty in the parameter estimates increases as the information decreases. And also similar, and the optimal locations of the sensors does a better estimation in damage. For example, here we found that the instrumented floors, okay, the instrumented floor. So here we did a damage detection. So we reduced the stiffness of the third story here by 28%. And we estimated the distribution of the ratios of the stiffnesses. We estimated the stiffnesses and the ratios, okay, of the stiffnesses. So the ratio of the stiffness shifts from 1, that basically indicates damage. So we have this combination number 3, which is the combination number of instrumented floors, and combination number 4. For the story stiffnesses, the combination number 4, which is 2, 3, and 4, was found to be optimal. Combination number 3 was non-optimal. And as you can see, in this case, at the location of the damage, okay, both combination number 3 and combination number 4 shifts. But at other locations, also combination number 3 shows a shift, showing false detection of damages, false alarms. And here, if you actually compare the means, the combination number 4 of instrumented floors shows a more closer to the damage that we introduced, which was approximately 28%. Okay. And also, if you can see that the uncertainty, the distribution, the density functions of these ratio distributions are thinner for the combination number 4 as compared to the combination number 3. So the uncertainty in the non-optimal location is more. Okay. We applied also this to optimal locations, sensor locations for non-classically damped systems. We extended this to non-classically damped systems, where essentially we wrote the response using the basically using the convolution of the input and the impulse response. And we had 2 expressions, one where we wanted to estimate the complex modal parameters, and other one where we wanted to estimate the physical parameters, which was in A and B, and C and D. So we assumed the measurement noise to be 0, mean Gaussian, and covariance matrix proportional to identity, and the fish information matrix turns out to be basically a product of the sensitivities of the responses with respect to the parameters of interest, where the responses we can estimate using this or using this. Both of them essentially are the Duhamel's integral. Okay. And the V and lambda in this case contain the complex modes. Okay. And then we maximize the determinant of the fish information matrix to get the optimal sensor locations, which are in P0. So which P0 basically maximizes the fish information. And we tested it in the lab by creating a non-classically damped system as the primary secondary system. So we have this frame that we had earlier, and we introduced a secondary system over here. Okay. In between, over here, in between. So the primary secondary system has different damping characteristics and will create a non-classical damping. And you can see here, that we plot the mode, the phase angles of the identified complex modes on the unit circle, and it shows that the modes are basically non-classically damped. So they are not falling on the components, and the phase angles are not 0 and 180 only. They show different values. Okay. And we estimated again the optimal sensor locations and the non-optimal sensor locations, and using the and we estimated the parameters for both the situations, optimal sensor locations and non-optimal sensor locations, and we computed the pulse responses using those parameters. And this is for the non-optimal, and this is for the optimal sensor locations. The pulse responses for the 6 degrees of freedom, the 4 of the primary system, and 2 of the secondary system here and here. So the secondary system had 2 floors basically, and was connected to the primary system's floors. Okay. And as you can see, the optimal sensor locations, so these gray ones are basically the uncertainty. So that shows a much smaller uncertainty when you compare with the non-optimal locations, especially for the secondary system. Okay. So optimally locating gives a parameter estimates which are much more which has much less associated uncertainty with them. So basically I will stop here. So summarizing, we talked about the uncertainty Kahneman filter for parameter identification. We introduced we showed that incorporating constraints to the constraint gain or truncated UKF leads to better convergence and less requirement of initial tuning. We showed some examples on RC frame, train bridge system, and the rocking systems. We discussed modal identification and physical parameter identification associated with that, the issue of identifiability when we have incomplete instrumentation, and we discussed a test for local identifiability with some requirements for global identifiability in case of shared type systems, and some tests for local identifiability using the implicit function theorem, which is applicable for any linear system. And then finally, we also discussed the optimal input-output locations, which was obtained by maximizing fish information in different cases, optimal input locations, sensors for non-stationary based excitation, and for non-classical dam systems. And we showed that it reduces the uncertainty in the parameter estimates and improves damage detection. So I will end by thanking my students who have done most of the work, excepting the identifiability part. They have basically been doing most of the work, and the different funding agencies who have basically funded most of the experiments that we have done. Okay. So I will take questions now. Thank you.
Thank you so much for such an engaging presentation. We will open it up for the audience. Feel free to type your question or raise your hand so you can ask your question directly. We are limited on time, but we thank everyone. And if it's okay, I think it will be great if we can stop recording so that people feel more comfortable asking questions. So I'll go ahead and stop the recording.